Rahim. Okay, now we are going to start the lecture. Okay, I have shared my screen and I hope you can hear my voice. Okay, ji, Bismillahirrahmanirrahim ji. Welcome to week 2 in steel structures. Okay, and in this lecture we will talk about the design philosophies which we will follow for the design of steel structures. Okay, like in the coming class we will discuss the design of different structural steel members like tension member, compression member, beams. So in order to design those structural steel members, we have to design it with certain procedures or design philosophies. So we will discuss about those philosophies in this lecture. Along with this, this is the main objective of this lecture. But apart from the design philosophies, the content distribution of today's lecture is also given. So you can see that after discussing having exposure to the design philosophies, we will talk about loads, okay? And we will talk about live load, dead load, and environmental loads. And in the environmental load category, we will talk about the wind load and earthquake load, okay? Then we will talk about the same design philosophies, and in the design philosophies, we will have some introduction about the factors which are used by two different philosophies, okay? Then we will see the different load combinations. Then we will go through an example, okay? How to use these load combinations using these two distinct design philosophies. Then we will make a comparison between an LRFD and ASD, like what is the comparison of these two procedures, and we will do it for a tension member case. And finally we will end our lecture on the emphasis that why we should use LRFD design philosophy. What are the benefits of using LRFD philosophy? Okay, so with this I will move on to the next slide. I hope you are clear with the content of today's lecture, that what we are going to discuss in this lecture. So the first is the design philosophy. I have already mentioned to you that there are two types of design philosophies, okay, which we will follow in this course. These are known as ASD and LRFD. You guys will be familiar with these two philosophies. I hope you have studied something about these philosophies in your concrete design courses. So basically there are two design philosophies, and we will use these two design philosophies for design or analysis of our steel members, okay? So these are known as allowable stress or allowable strength design and load resistant factor design. But first we will talk about the ASD design philosophy or allowable strength design procedure or philosophy, okay? Allowable strength design procedure is also known as elastic design, or it is also known as working stress design, okay? Okay, in ASD or allowable strength design philosophy, the cross-sectional dimensions of the members are selected so large that the effects of the loads or the stresses that are produced in that any member remain within the permissible limit, okay? Now, like we select a large cross section, we know that a member derives its resistance from the material property and from the geometry or cross sectional geometry. So we select the cross sectional area of the member so large that the stresses or the effects of the loads which are produced in the member remain within the elastic range or the permissible range, okay? So the applied loads can be axial forces, it can be shear forces, it can be bending moments, okay? Now these forces will produce some effects in the member, okay? these member effects can be axial stresses, shear stresses, bending stresses. Okay, now these stresses has to be resisted by this member, and this member resists these effects with through its cross-sectional dimension and material properties. Okay, now we select such a large cross-sectional area in ASD that the effects which are produced by this axial, shear and bending stress loads are remain within the permissible value, and the permissible value we consider permissible value as the elastic range. Okay, now in the ASD procedure or philosophy, the allowable value is obtained by dividing the nominal, which is also called the theoretical strength, by a factor of safety. Okay, now in ASD we make usage of a factor of safety. Okay, so what we do that we reduce the resistance of the member. Okay, like the theoretical resistance is there. Okay, now we reduce this theoretical or nominal strength by dividing it by a factor of safety. So in ASD philosophy, we make usage of factor of safety. Okay, make usage of factor of safety. Okay, so, and the basic philosophy of the design is that capacity of the member. The capacity of the member should be large or at least equal to the demand. Okay. Now this demand, we can also term it as the required strength of the member. Okay. And this allowable is strength is representing the capacity. Okay, now as I told you that the capacity we reduce the capacity of the member, or we reduce the resistance of the member in ASD procedure. Okay, by dividing it by a factor of safety. Okay, now this strength, allowable strength, can be an axial force strength. As the members, we will see that when they are subjected to tension or compression, or this strength can also be a flexure strength, or it can be a shear strength. Okay, now this allowable strength design is also sometimes called the allowable stress design. Okay, if you use the word stress instead of this strength, okay, so we will term this procedure or philosophy as the allowable stress design philosophies. And this equation, this equation will turn into a different equation in terms of stresses, like what is the allowable stress and what is the maximum applied stress. Obviously this is derived from the loads. Okay, this is derived from the loads, and this comes from the resistance of the material. Okay, and the resistance of the material comes from the cross-sectional area. Okay, like the cross-sectional area. Okay, cross-sectional area, it comes from the material properties such as Fy. Now this is like allowable strength design and allowable stress design are used interchangeably. Okay, now as I told you that this allowable strength design or allowable stress design, we also call it elastic design or working stress design. Okay, now what this approach is to design is called elastic design or working stress design. Okay, now what are the working stresses? Working stresses are those stresses which are resulting from a service load. Okay, like when the loads are service loads, so the stresses which are produced in the member, we call them the working stresses. And what are the working loads and the working stresses are always elastic, because we keep the member or resistance so high that the stresses which are produced in the member remain elastic. Okay, now one thing to note in this slide is that ASD make use of factor of safety. You divide the resistance of the member by a factor of safety, but In other words, you can say that in ASD, we reduce the resistance of the member by dividing it by a factor of safety. Okay. Now, as I told you, I will elaborate that ASD procedure. Like, for example, we have a member, let's say it's a truss member, for example, and it is subjected to tension. And the axial load, which is passing through the centroid of the member, it's a concentric load. Sorry, this is not an eccentric load. Okay. Now this is P. Okay. And the cross section of this member is a rectangular section. Okay. It's a solid section. Okay. And the cross sectional area of this member is A. And if we see what are the axial stresses, which are produced in this member due to the application of this load P. So we will term it, for example, say these are the stresses sigma, and this is P divided by A. Okay. Now this, you can see that the area is in denominator. If we increase the area, stresses will be reduced. Okay. Stresses will be reduced. Like this is inversely proportional to the stresses. Like this area component, which is in the denominator. So what we do in ASD, that we increase the geometrical cross section of the area. Okay. So when we plot this stress, okay, it will produce some stress in the member, and obviously it will also produce some strain. And when we have we look at the stress strain curve of this member, a tension member, initially it will be elastic. Okay. Then it will okay. Then we will have some strain hardening, and then we will have some degradation in the strength. Over here it will rupture. So on the y-axis, let's say this is the sigma, and on axis we have this epsilon. Okay. Now this is the strain and this is the stress. Okay. So in the case in ASD procedure or ASD design philosophy, we keep our stresses within this permissible range. Okay. This is permissible range. Okay. This permissible range, we term it, or we also call it elastic range. Okay. Elastic range. So we keep the stresses or the effects of the loads within the elastic range. Okay. Your stresses should be somewhere in between, in this region. Okay. It should be in this region. Okay. Not in this region. Okay. And in order to accomplish that, we use a large cross-sectional, or we use a member with a large cross-sectional area. Okay. Is that okay with all of you? आप लोगों को समझ आ रही है? Are you following me?
Yes, sir.
Okay, thank you very much. Okay, so this is ASD. Okay, now ASD, what we do that we divide the resistance. Okay, I'm sorry for my resistance of the member. Okay, resistance of the member by factor of safety. Okay, resistance, and this resistance it derives from the cross-sectional area, or in other words, you can say that this resistance, the member derives it from its geometry. Okay, cross-sectional area and the material properties. Okay, material properties such as Fy. Okay, material properties. Okay. So the stress is the basic ideology of ASD is that the stresses in your member should remain within the elastic range. Okay. So this was all about the ASD procedure. We have another procedure. Okay, and the loads which produces these stresses. Yes. So these loads are called service loads. Okay. This is service loads. Okay, service loads. Service loads. Okay. Oh, we have another philosophy apart from the ASD. We have slight extension of ASD towards LRFD. We call this philosophy the plastic design philosophy. Okay, what you do that you have this stress strain. This is the behavior of a member, let's say the same tension member. So what will happen that the loads will be in the elastic range. Okay, loads will be here, but you design your member for this plastic range. So this is the stress and this is the strain. So you divide your you design your member for loads such that the stresses in your member should be at the verge of plastic. Like there are plastic stresses that will be induced in the member in the plastic design. And how do we accomplish that? What we do that we multiply the service loads. Okay, this is service loads by some load factor. Okay, load factor, you increase the loads. You, in other words, you can say that you enhance or increase the load, enhance the loads. Okay, so that when this load is reached, your member will fail, as the collapse of the member will occur, or you will have an excess. So yeah, let me collapse. It will result in collapse or excessive deformation. Okay. So you design for a load in plastic design such that the stresses in your member should be in the plastic range. Okay, when that load is reached, the plastic stresses, the stresses that will generate in your member will be plastic. Okay, so let me this is the plastic design. Okay, now, in the plastic design philosophies, as I told you that stresses are in the permissible limit, okay? But we increase the load, okay? So that the stresses in the member at the verge of failure, okay? Now, let me go back here. So we design our members so that the design loads are here. We design for these loads. We design for those loads which will produce stresses which are in the plastic range, okay, not in the elastic range. Okay, and how do we accomplish it? We multiply the loads with load factor. Okay, and we do not use any safety factor of safety in plastic design. Okay, no factor of safety is used. Okay, now you will see that this is plastic design is based on the criteria that failure conditions, like the plastic design is based on consideration of failure condition rather than the elastic load condition. Okay, a member is selected using criteria that structure will fail at a load. Okay, structure will fail at a load substantially higher than the working load. Okay, and that failure will be demonstrated in terms of collapse. Okay, or in terms of large, extremely large deformation in the member. Okay, and how do we accomplish this? How we do this plastic design? We increase the working loads or the surface loads. Sorry, service loads. Sorry, by multiplying these service loads by a load factor to obtain the failure loads. Okay, now what we do, we determine the cross-sectional property of the member needed to resist this load. Okay, we do not design it for the load which is workable load. Okay, we design it for the failure loads. Okay, or the plastic load, you can say. Okay, okay, what happens that members which are designed by the plastic theory would reach the point of failure under factor load, but are safe under actual working load. As I told you, the loads in the member will be in the they will be service loads. But what you do, you enhance the loads, okay? You enhance the actual loads so that they correspond to the plastic region of your member, okay? So now the second distinct philosophies you guys have been using, we call it LRFD, or load resistance factor design philosophy, okay? Now this LRFD philosophy is similar to the plastic design philosophy, okay? Now in the LRFD you also consider the failure condition, but let me remind you that in the plastic design, how do we increase the loads? Like, how do we get the failure loads? We multiply the loads with a certain load factors. And in LRFD, we also do use the load factors. We multiplied these load factors with the surface loads, okay? And then member is selected that have enough strength to resist these factor loads, okay? Now, one additional thing we do in LRFD is that we not only use the load factors, but we also reduce the resistance of the member by multiplying it by a resistance factor. And the basic equation in this LRFD philosophy is that factored load, which has been obtained by multiplying different service loads, with some load factors, and these load factors are different for different kind of loads. And at the same time, what we do that factor strength or the resistance, what we do, we use the usage of factors we call resistance factors. Resistance factors are multiplied with the strength of the member, okay? Strength of the member or the resistance of the member, okay? Now these load factors are most of the times they are greater than unity, or almost they are greater than unity. Like you will see the load factor as 1.4, 1.2, 1.6, but the factor strength, or in the factor strength portion, the resistance factors are always less than 1, like 0.8, 0.7, 0.9. And this is further elaborated here. This factored load is this much. It is the summation of all the loads with their load factors which are acting on your building, okay? This factor strength is the resistance that is multiplied with the resistance factors, and these resistance factors are less than 1. You are reducing this resistance, okay? These load factors are always greater than 1, okay? Now what happens that whenever these factored loads are applied to the your structure, what will happen? It will push the structure to its limit state, okay? Now there are different limit states in steel structures, so you will see it in the coming class when we start discussing the connections, okay? Now these limit states you should note down. These limit states are fracture, fracture in the material, yielding in the material, buckling or the stability failure. And at the same time, if there is an excessive deflection in your member. So when the loads are applied to a member or a structure, so it will, when the factored loads are applied to a structure, so the structure will reach its limit state. And what are those limit states? Fracture, yielding, buckling, excessive deformation. So you should remember that, okay? Basically, this was all about those design philosophies. This is just a summary, like I have discussed this slide with the section B as well. Like Like what is ASD? Like ASD is the allowable stress or strain design. Okay, plastic is an extension of ASD because we are going from ASD to limit state design. And the most recent form of limit state design, we call it LRFD. Okay, in ASD, the stresses remain within the elastic range. In case of plastic, the stresses are in the plastic range. Okay. Now we know that whenever we design our building, okay, we design it, the building lifetime is 50 years. And in the 50 years, you have to consider the maximum effect of loads. One, like if you are considering the maximum effect of one dead load, but it should be coupled with the live load, it may be coupled with the snow load. Okay, so these loads actually produce some limit states. These are fracture, yielding, buckling. Okay, now ASD or in plastic design theory or approach, we do not use any resistance factor. Okay, now before the next up is the loads. Okay, but before going to the loads, there is a definition of structural engineering. Okay, this is just an elaboration of structural engineering, like what we call structural engineering. Structural engineering is the art of using material to build real structures so that they can withstand the forces which will be exerted over it, okay, during its lifetime. The important thing you should note that the art of using material, the material properties are only estimated. Okay, the analysis techniques we use to analyze our structures are approximate, and the loads which we use, they are not accurately known. Okay, so we should exercise care. Okay, in order when we go for this, all should be in our mind whenever we are going for a design of any structure. Okay, so loads, as I told you that during the lifetime of the building, the loads, there will be different type of the loads which will be acting over your structure. So we can classify them as dead load, we can classify them as a live load, we can classify them as a environmental loads. So dead loads. Okay, now what are the dead loads? Like the weight of the structure, weight of the permanent machinery, and the loads, the position of the loads which are fixed. Okay, so we call all those loads as the dead loads. But in order to have a fair definition, like what we have to consider as a dead load and what we have to consider as a live load, or what we have to consider an environmental load, so you need some document, and that document we call, or we know that, which is the most recent code, that is International Building Code. So you have to go to that code and you have to see that what is the definition of dead load. In case of Uniform Building Code, you can refer to section 16, and that will tell you that what members of the structure you have to take it as a dead load. Okay. Similarly, the live loads are the weights of the people, the furniture, the machinery. But in order to have a very specific definition, what types of the loads you will consider live load, you can refer to the code. Okay, you should consult a code. Without using a code, you cannot design. Okay, you cannot design structure by looking at these lectures, our lectures. So they are most of the time we may have missed something, so you should consult a code, right? The code you will consult is the IBC. Okay, now the live loads are the weights of the people. Okay, they are the weights of the occupants. Okay, now the live load depends upon the building. Like if you are designing, if you're building, the purpose of the building is a school, if the purpose of your building is a library. Okay, if the purpose of your building is the residential building, the magnitude or intensity of the live load is different. Okay, now these live loads are mentioned in these codes. Okay, for example, let's take an example. We will refer to the UPC code. So in UPC code, so the type of the buildings and the live pounds per square feet, but you can consult table number 16A, but you should now consult IBC. Okay, this is obsolete now. Okay, so the residential building, the live load is 40 pounds per square feet. For library, it is 60. For heavy storage, this is minimum to 50 pounds per square feet. When you design your building, you have to take the live loads. Okay, these live loads comes from the codes. Okay, so the third category of the load is the environmental loads. And the environmental loads includes wind load, snow load, rain load, earthquake load, flood load, but our focus will be on the wind load and the earthquake load in this category. One important thing is that whenever you are designing your floor, a classroom, for example, in a school, and your building is a school, and a classroom has a area which is greater than 150 square feet. So what you do, you will reduce your live load by multiplying it by a reduction factor, and that reduction factor is given by this formulation. So how do you calculate it? So this is, you can use this formulation. You have to use this formulation to reduce your live load. And how do you reduce it? You just multiply this factor with the live load. If the area which you are designing or which you are considering live load is greater than 150 square feet. Okay, I will stop here. I will take a breather. Now, this is Ramazan, so you think of some questions so we can discuss them as well. Is it good? So we can take a break, a pause for 3 minutes or 4 minutes. Is that okay with all of you?
Yes, sir, it's okay.
So you think about it, what I discussed, okay? You think about design philosophies. You think about what live load and dead loads and environmental load. So I will take a breather because my throat is almost dried out, okay?
ओके सर।
आप लोगों को समझ आ रही है जो मैं ये बातें कर रहा हूँ? मतलब is that okay with all of you?
Yes, sir.
Okay.
यस सर।
Okay, thank you. So let's take a pause for 3 to 4 minutes, okay? Okay, we are going to start. Okay.
एक्सक्यूज मी सर,
Yes, please.
ये आपने जो रिडक्शन फैक्टर की बात की, इसका एडवांटेज क्या है?
Advantage, like, you know, these factors or these loads have been determined as a result of experimental work. Okay, the load factors what you see is 1.2 or 1.6, they have been derived by a probabilistic theory, we call it reliability theory. Okay, so there are some factor of safeties, like they have considered that if the member, they have carried out a study, okay, based on their study, that if the member or the cross-sectional area of your room or hall what you are designing is more than 150 square feet, if you apply that load, what will happen, that this will be overestimation of the load, in my point of view. Okay, this is my opinion. Okay, that's why they want to reduce it. Is that okay with you?
Yes, sir.
But I will check with somebody else as well. Okay, I will have another opinion as well.
Okay, sir.
Okay.
Yes, sir.
Okay. Now, as I told you that we will discuss the environmental loads, and in environmental loads, we will focus on the wind load. Okay, wind load is a lateral load. Okay, and wind load exerts dynamic pressure on your structure. Okay, and this dynamic pressure you can estimate it with using a Bernoulli formulation. Okay, now in the Bernoulli formulation, you have wind speed, you have the like wind, like means the fluid speed, you have the unit weight. Okay, now the dynamic pressure that is exerted by the wind on the structure can be estimated by this Bernoulli equation. Okay, now this equation does not account for the gust, or it does not account for dynamic response of the body. Okay, so the wind speeds, okay, whenever we design for winds, okay, now these winds correspond to certain return period. Okay, and if we look at the IBC or our code, so the wind first of all, where is this pen? Let me grab my pen. Okay, wind speed, you have seen that this, you can use it using Bernoulli equation. Okay, like this one. Okay, so from where you will derive this wind speed? Okay, wind speed, you can use maps. Okay, wind speed maps, okay, and what are they? The wind speed maps or wind velocity maps correspond to certain probability of accidents during the lifetime of your structure. And the design maps or wind speed maps which are used in IBC or which are used in the loading code. What is the name of the loading code? ASCE 7. So it recommends usage of some maps. Okay, these maps, obviously this code is for USA. Okay, now this code suggests to use some maps, wind velocity maps. Okay, so these maps have been developed for 7% of chance of accidents in 50 years. So you should design your structure for wind speed which corresponds to 7% of chance of occurrence in 50 years, or it should have a return period of approximately 19 years. Okay, you should use that wind velocity for design of your building. Okay, and these maps, you will see that if you go through these codes, they correspond to velocities which are measured at a height of 30 feet. Okay, So these measurement of the velocities first has been made by at different observatories or the meteorological stations, and the number of meteorological stations what I have seen is 485, and then they have used probabilistic theories to develop these maps. Okay, now these maps correspond to certain return period, and these velocities have been measured at certain heights. So this height is considered as 33 feet high. Okay, now the velocity measurement has been made at 33 feet height, and the same is recommended by the UBC. Okay, what this slide is showing that the wind pressure which we use in design should be based on wind velocity having specific recurrence period. Okay, what is that recurrence period? 7%. Okay, 7% chance of accidents. Okay, and why do we consider 7% chance of accidents in 50 years? Why 50 years? Anybody from the class?
बिल्डिंग लाइफ कितनी होती है?
Yes, the life of the building is considered as 50 years. So during the entire life of this building, you should design for that wind which has a probability of occurrence of 7%. Chance of occurrence or chance of possibility of 7%. Okay, this is solely probabilistic term. So you will see that in earthquake we also design our buildings for ground motion which correspond to different probability of accidents in 50 years. So we will discuss them in coming class. Okay, now okay, now what happens that wind velocity, the flow of the air close to the ground is slowed down by the surface roughness, which depends upon the density, size of the building, trees, vegetation. Okay, like what is trying to say that the velocity of the air, if this is the ground wind, it is slower at near the ground, and this velocity is also getting affected by the surroundings where you are constructing a building, your building. It is also, this velocity is also getting affected due to the roughness of the ground, the topography of the ground. Okay, now this topography, you can see that this is an example of 100 miles per hour velocity of the wind. If you are building your structure is located in a large city, so this will be the profile. Okay, variation will be different. And for example, you are building your building in outskirts of city, so this will be the variation. Okay, and if you are building your building on a coastal belt, so open flat area, so this will be the variation. Okay, the ground velocity will be not that affected by these obstructions. Okay, so wind velocity, okay, what this slide is showing that wind velocity profile over terrain with different roughness characteristic. Okay, for uniform gradient. Fine. So whenever we are designing our building, or the design pressure which will be exerted on your structure, it also depends upon the shape of the building. For example, if this is the wind, let me grab my pen correctly. If this is the wind and it is subjected to a circular building, so it will not exert that pressure on the building. I'm sorry for my drawing. Okay, shape also affects the wind pressure. So but if your building, if we see the cross section here, so let me see, if this will be a circular, if your building is a rectangular or square, so it will experience more pressure. Okay, in order to take the shape of the building into the account, okay, and the horizontal angle of incidence of the wind, so we use different factors. Let's see, we call them CS. Okay, now CS is for windward face or flat roof rectangle building is 0.9, and this value is coming from UBC. Okay, this is coming from UBC 97 code. and you will see the different, like CS value is different for windward side, and CS value is different for the leeward side, and for the sides of the building this value will be different. Okay, so let me draw it here. Let me draw it. Just give me a moment. Okay, I have to delete this stuff. Okay, this one. Okay, over here, yes. Yes, now that's okay. Yes, that's fine now. Yeah. For example, this is a building, for example. Okay, let me. This is a building. Okay, and the wind velocity is in this direction. Okay, this is the wind velocity. Okay, and what will it do? Okay, so the cross sectional or the dimension is like this. Okay, so in this direction which is facing the wind speed. Okay, so this direction of the building we call it windward side of the building. Okay, windward side. This direction we call the leeward side. Okay, leeward side. Okay, so on the windward side you will have some push due to the wind, or we will say that over here you will have a pressure on the building. Okay, there will be pressure on the building. Okay, to this side of the building you will have suction. Okay, in order to further elaborate it, let me, if I can see, I can draw. For example, this is the plane of the building. Okay, the same building. Yes, wind is in this direction, so it will exert, this wind will exert pressure on this side of the building, and to this side of the building will experience suction here. Okay, over here we have suction. Okay, to this side we experience the pressure, and similarly to the sides of the building you will also experience suction. Okay, suction. Just remember that this represents suction. If you are facing this direction, this point, this will pressure. If you are facing this point, so this will this we call suction. Okay, so you will see that there is a building. Let's say this is a civil engineering building, and wind velocity is in this direction. To this direction, you will see pressure. This face of the building will experience pressure. This face of the building, which is not facing the wind direction, will experience suction. Okay, and similarly this side of the building will also experience suction. This will also experience suction. Okay, and you can calculate this using this formulation. Okay, you just have to multiply the Bernoulli equation with this CS coefficient, the shape coefficient. Okay, now this is an explanation to this what I have discussed, that in case of pressure, if the side is facing towards the wind direction, so pressure will act on the windward side, and this side we call windward side. Okay, this is windward side, windward. Okay, this side we call leeward. Okay, so you guys should be familiar with this terminology. Now it says that section of the building, so a person standing in the window may be thrown outside. Okay, like in over here we have suction, to this side we have suction, so this will try to pull anybody standing in this window. To this side you will also experience suction, and inside the building you will also experience suction. Okay, like you will experience this kind of pressure. It will try to blow the roof. Okay, the floors will be experiencing suction. Pressure to the windward side
and at other sides of the building, inside the building, you will experience suction. Whenever wind is acting on your structure, there will be pressure on the leeward side, and on the rest of the sides and the inside of the sides, you will have suction. Okay? Is that clear to you?
Yes, sir.
Okay, now we will talk about the bridges. Okay, in bridges, what happens that, for example, this is a truss bridge only. Okay, we know that wind is blowing in this direction, so this is the windward side. Okay, and this side is the leeward side. So what we do, as per the H2 specification, we neglect suction on this side, and we consider this truss as a solid cross section. We know there are some open spaces here, but we consider it according to the code as the solid without opening, and we apply the pressure, and we design for this pressure, this bridge. Okay, now you have to neglect the suction on the leeward side whenever you are designing a bridge. Okay, you don't have to consider the suction. Now, as I told you that we have discussed two different procedures in order to estimate the design wind pressure. This is the second procedure. The first procedure is that whenever you want to estimate the wind pressure, so you can use this procedure, CS into Q, and that Q is rho times velocity of the wind divided by 2. But there is an alternative procedure you can also use, and it is also coming from this UBC code. You can use this formulation. Okay, now this is the CE is the height of the building, exposure and gust factor. Okay, gust is the turbulence in the wind velocity. Okay, CQ is the pressure coefficient. This is for the shape of the building. Okay, now we have some at 33 feet. We have this pressure, and this value it's about 23 pounds per square feet. And we also have some importance factor. If you have to go to the code and you have to multiply it together, and then you will get a pressure. Okay, so this is very simple. If you go to the code and you pick the values relevant to your building type, relevant to the exposure type of your building, and then you can compute the pressure using this formulation as well. So as I told you that we can use simple formulation in order to compute the design wind pressure. So we know that this is that CSQ, and CS is rho V square by 2. If you take the unit weight of the air, this is the unit weight. Okay, if you plug the unit weight value here, so it will come out to be this number. So if you go to the code and, for example, you have to calculate the wind pressure for a velocity of 100 miles per hour, and your civil engineering department is subjected to this pressure. So how you will compute the pressure? So we know that there are two sides, windward side, leeward side. Okay, so we have neglected the sides of the building. We are just considering the windward and leeward, and we have to go to the code, and based on the characteristic of this building, you have to come up with CS values. Okay, inward and outward. Okay, so you can consult the table 16H in the UBC, and you can compute the wind pressure. Okay, using this formulation. Okay, you can use this formulation as well, that I told you that there are two procedures. So you can pick the values, and similarly you can compute the pressure. This is the windward pressure, this is the leeward pressure. Okay, so next up is the in the line is the earthquake load. Okay, now as you know that earthquakes are produced due to the rupture along the faults, And during the rupture, what happens that strain energy is suddenly released. That energy is transformed into some waves. Okay. Now, basically, there are two types of waves. We call them body wave. We call them surface waves. Okay. Now, these waves, now what we experience shaking as a result of these waves. Okay. Now, there are two types of body waves. We call them P wave or primary waves, or the secondary waves, or the shear wave. Okay. Now this slide, this is telling us that where the shaking that are experienced by the structures and the people who are standing on the ground is due to the propagation of the waves. And not only these body waves, but there are some surface waves. And the surface waves are the Rayleigh waves and the Love waves. Okay. So now this is just a demonstration of these body waves. Okay. In the body wave, the particle movement or the material through which it is passing, the movement of the material will be parallel to the propagation of the wave direction. Okay. Like the particle, the material will be also moving in this direction, and the wave is also traveling in this direction. In case of the S wave, the wave is traveling in this direction, but particle will be traveling in this, movement of the particle will be in the vertical direction. Okay. The movement of the material particle will be in perpendicular direction, but the propagation of the waves will be in the horizontal direction. The P waves are the most fastest waves. They are they can travel through any material. They can travel through liquids. They can travel through the solids. S waves can only travel through the solids. Okay. So the P waves travel in the form of compression and rarefaction. The S waves travels in the form of crust and troughs. Okay. Now, whenever your building is experiencing ground shaking, so there will be some seismic forces which will be generated in your building. Okay. Now, the response to any earthquake of the building depends upon the mass of the building. Okay. If the mass is more, more inertial forces will be generated in your building. It depends upon the response of the building, depends upon the overall stiffness. It depends upon the natural period of the vibration. Like your fundamental period should not match with the time period of the waves. Otherwise, it will start a phenomena we call resonance. Okay. Now, the response of the building also depends upon its energy dissipation characteristic, which we call damping. And it also depends upon the location of the building from the epicenter, and the topography and geological formation. For example, your building is located on a mountain. So what these waves will start converging at this point. So over here you will experience more shaking as compared to at the foot of the hill. Okay, the topography is important. For example, you are building at structure at a very loose deposit. So loose deposit tend to amplify the ground motion. They tend to amplify the amplitude of the waves. So you will experience more intensity shaking. And if you are building your structure on a hard soil or rocks, so you will experience less shaking. Okay, location from epicenters means that if you are far away from the earth epicenter, you will experience less shaking. Okay, because the amplitude of the waves is attenuated when they reach you. Okay. Okay. Now we will discuss the earthquake design procedure. Okay. Now there are different procedures which are mentioned in the codes. We can use them to evaluate the seismic response of your building. They are known as response spectrum analysis. They are known as pushover analysis, time history analysis, and the most simplest procedure we call it equivalent static procedure or static lateral force procedure. Okay. Obviously, you know that in your building you should not have those irregularities, the plane irregularities and the vertical irregularities. So this slide is showing that static limitation of static lateral force procedure. Okay, for what kind of buildings this procedure is applicable. Okay, for example, all the structures which are regular. Regular means they do not have those irregularities. Okay, or irregular. Okay, they have irregularities and they are located in seismic zone 1 and in the occupancy category 4 and 5 and zone 2. Like this procedure is relevant, or it can be used for all those buildings which are either regular or irregular and they are located in zone 1 or zone 2. Okay, now it can be adopted for regular structure up to 240 feet height. Okay, now these are some of the limitations, you can go through them. Okay, this is another limitation of this static lateral force procedure. Okay, now basically if you want to evaluate the response or the forces for which you have to design your structure or your building, you have to calculate the base shear, and using equivalent static procedure you can calculate the base shear by this formulation. V is equal to CVI by RT into the weight of the building. Okay, now this is called the base shear. Okay, design base shear. So there is an upper bound to this base shear. This base shear should not exceed this value. Okay, and it should not be less than a particular value. Okay, and if you are designing or your building is placed in zone 4, then you have to use this formulation in order to compute the design base shear. Okay, in case you are designing your structure and it is lying in zone 1, zone 2A, zone, and so then you should use this formulation in order to calculate the base shear which will result from the earthquake or when shaking, when your building will experience the shaking. So you should compute the forces, the design base shear which will be generated in this building through using this formulation. So this is coming from the code. Okay, there is a lower bound, there is an upper bound. So for example, your building is located in zone 4. Okay, so then you have to use this formulation. Okay, but you have to multiply a factor with the weight. Okay, this R is the response modification factor, I is the importance factor, T is the fundamental time period of the building, and CV and CA are the acceleration and the velocity coefficients which you can obtain from the code. Okay, so this is like what is V? V is the total base shear. What is CA? C dynamic response values. Okay, so you can take these values from this table from the UBC. Z is the seismic zone factor you can obtain from this table. NV and A, which are the near source factors, okay, which are only applicable in zone 4. If your building is located in zone 4, then you use these tables in order to get these values. So there are different categories of the soils, like for example, wherever you are building your structure, for example, where is this one? For example, you are building your structure somewhere, you need to know the underlying soil. Okay, you have to classify this soil into different categories. You have to select it. Is it SA? Is it SB? Is it SC? SD? E? and F? Okay, so this definition of SA and SB is based on some measurement of shear wave velocity in the soil. Okay, and it can be also for C up to E, we can also obtain it using the SPT number or the undrained shear strength. So it is very important to know the soil category classification over which you are building your building. Okay, so you have to carry out some testing and you have to come up with the stiffness value of your soil, and based on the stiffness value you can classify it as a hard rock, rock, stiff soil, or soft soil. Okay, so the building code of the Pakistan have been adopted from the UBC 97. So there are certain zones, seismic zones. There are 5 zones. There are zone 5, 1 zone, 2A, 2B, 3, 4, and these zones have some intensity values, and these intensity values are in terms of PGA values. Okay. So based on your map, like the wind velocity map, you should also have the peak ground acceleration map. Okay. For example, peak ground acceleration again. Map. Okay. For example, you are constructing your building in Pakistan, so it should be, you should have this map for Pakistan. On that map, these zones will be marked, and based on the location of your building, you can select where your building is falling. Is it falling into zone A, zone B, zone C? Okay. You can estimate the, as I told you, that this is I in the base shear formula is importance factor. W is the total seismic load. R is the response factor, okay, which depends upon the structural system. Like for example, you are using a moment resisting frame. Is it IMRF? Is it OMRF? Okay. Is it ordinary moment? Is it special? SMRF? Okay. So based on these categories, you can select the response modification factor. You can estimate the fundamental time period of your building using this empirical formula. For steel structure, you need this coefficient, which is 0.035, and you have to multiply it with the height of the building. Okay. So in order to estimate the fundamental time period of vibration for your building, and this period, this R value, this weight, this I, you will use it to compute the base shear. Okay. So this is just a definition of the explanation of the base shear formula. Like in the base shear formula, what it is called, this is coefficient is all dependent of the period of vibration. It is the lower bound value, okay, on the base shear. Similarly, this is called acceleration factor. This coefficient will govern the building with medium to long. These are some of the certain things from the code. Okay. So this is just an explanation of these base shear formulas. Okay, different factors which have been used in the base shear. This is what is this factor? This is a lower bound. So you can go for the, you can go to these slides, and you can look at these slides. What is the lower bound? What is the upper bound in zone 1, 2A, 2B, 3? Okay. Okay. So this slide is showing the base shear for the masonry structures. Okay. Now, what are the base shear coefficient for the masonry structure? If you are constructing, if this is located in zone A, if it is located in zone B, you have to use this base shear value, this base shear value, this base shear value. Okay. Now, this, once you have computed the base shear, you can calculate the different forces which will be acting on your building. For example, where is that? This building. So you can compute the distribution of the forces at different stories. Okay, using this formulation. Okay, in this you have Ft is the plus summation of f of x. Okay, Ft value you can obtain from this formulation. And if the Ft value, if the fundamental time period of the building, which we have seen that we will estimate it using this C, what was that formula? Let me see, this CT, yes, CT. CT Hn 3/4. If this is less than 0.7, so Ft value will be 0. So then you plug in that value here, you plug in base shear, you plug in the weight of the story, height of the story, then you have summation of weights and heights of all the stories. For example, this is just a demonstration. You have a single story building, and the time period of that building is less than 0.7. So FT value will go to 0. Okay. So there is one story, this will cancel out with this one. So if forces that will act on the simple story, a single story building, will be equivalent to the base shear. Okay, this is F1 as well. Now, now we have an example. Okay, now you have to calculate and distribute the base shear for a 5-story residential steel building, which is 50 feet high, and it is located in Peshawar, and Peshawar is located in zone 2B. Okay, and zone 2B, the PGA value ranges from 0.16 to 0.24 G. Okay, you can calculate the base shear using this formulation, and you should also calculate the minimum value. You have to check, is it less than the maximum value, is it greater than the minimum value. You have to perform this value. You have to use some tables, like from tables from zone 2B, you have Z.2, CA, CV, these values, importance factor is 1. So building is ordinary moment resisting frame, so response modification factor can be 4.5. You should estimate the time period. The time period is less than 0.7. Straight away FT value will go to 0. You compute the base shear. Okay, so this base shear is like this value is here, this value is here, and this value is here. So this value is greater than this, and this is less, so this is correct. Okay, so you will use base shear, this value, this will be the base shear. Now we have 5-story building, 1, 2, 3, 4, every story have a different weight, they have different height, and this starts from the ground. Okay, basically you have to use this formulation. You have to plug this FT value equal to 0, and for example you are calculating F1, so you should multiply W1 into H1. Okay, then you have to divide with the summation of W1. So once you do that, so first you have to calculate the total W, total weight of the building, which is 82 kips. Okay, FT is 0, and story 2, story 3, story 5 have a 14 kips weight. Okay, 1 and 4 has 20 feet. Okay, now you can first calculate the total base shear using this value. Okay, W value. It's so lengthy. So you use this formulation to compute the F1 value. The F1 value is 0.92 kips. Similarly, you can do it for F2. Similarly, you can do it for F3, F4, F5. So this was all about earthquake loading, okay, or seismic loading. We talked about wind loading. We talked about earthquake loading. So these are the 2 types of environmental loads to which your structures will be subjected. So this is where there were some preliminary examples. So we went through 2 examples just to demonstrate that how you can use this formulation. Okay, so can we take a break? What is the time now? Guys.
Yes, sir.
Yes, sir.
Okay, I hope you are. I'm very glad to know that you are with me. Okay, so it was a bit lengthier, I know that. Okay, but we have to complete it. Okay, if you go through these slides, so you can easily understand. Yes, please. Okay, can we take a break?
Yes, sir.
Break for
Okay. So what time we should be back?
9:45.
9:29.
9:45 the break will be in.
Okay, I will slightly extend it this time. So we'll be back by 9:50. Okay.
Okay, thank you.
Thank you very much.